Currently, rocket fuel makes up about 70% of the weight of a rocket and about 80% of the cost. This makes rockets very expensive to launch, and it makes them very heavy too. Solar sails, on the other hand, are extremely light, and the materials can be very cheap. They use photons from the sun as their fuel, and they're limited by the speed of light. Although solar sails could not completely replace rockets, because rockets are still needed to get up and out of our atmosphere, solar sails could be used on longer space journeys, and they could potentially be propelled by lasers. CayugaSat would be a 3-unit solar sailing CubeSat. Its orbit around the Earth would look something like the drawing here. This orbit provides the most thrust in the direction that it's going around the Earth, and it eliminates any excess thrust that would cause it to move in the wrong direction. CayugaSat will deploy its solar sail using accordion arms. When these accordion arms are not deployed, they will be folded up and form a smooth surface, constituting the outer layer of CayugaSat. In all, there will be 388 segments making up these arms. They will be attached to CayugaSat with 90-degree rotating hinges. When the sail is deployed, it'll be 5.7 by 5.7 meters. Each segment of the accordion arm will be made up of aluminum alloy 7075. Each segment of the accordion arm will have 2 small ovals cut in it to reduce mass. These accordion arms will be deployed using a 4-way telescopic extender. This extender is made up of 4 mother compartments with 4 smaller baby compartments inside. These smaller compartments act like screws against each other. The end of the mother compartments have small gears on the end. When these gears are turned by an even bigger gear on top of them, it twists the smaller segments out and extends them, thus deploying the accordion arms. The smallest end of these telescopic extenders is connected to the first segment of the accordion arm, so when these are twisted out, it pushes out the accordion arm. Each telescopic extender, when extended, measures about 12 centimeters. CayugaSat would deorbit after its goal of a 40-day orbital period by simply using the direction of the photons coming from the sun to push it down towards the Earth. When it gets close enough to re-entry of the atmosphere, it would eventually contract its solar sail, thus re-entering and burning up. The mission of CayugaSat would include remaining at altitude or gaining altitude for 40 days and deploying the solar sail successfully in a technology demonstration. The budget for our CubeSat includes such expenses as power, communications, the actual sail and deployment, and structure. In all, it came out to be $6,908. Mission success criteria for CayugaSat are as follows, ranging from least successful to most successful. 1. CubeSat fails launch. 2. CubeSat launches successfully but is unresponsive. 3. CubeSat is responsive but cannot orient itself. 4. CubeSat orients itself but cannot deploy solar sail. 5. CubeSat orients itself, deploys solar sail incorrectly. 6. CubeSat orients itself, deploys solar sail correctly, but is unable to contract solar sail. 7. CubeSat orients itself, deploys and retracts solar sail correctly, but is unable to repeat this process. 8. CubeSat orients itself and deploys solar sail correctly many times. 9. CubeSat is able to use solar sail to maintain altitude for 40 days and then burn up upon re-entry. A likely timeline looks something like this, ranging from CayugaSat getting chosen as the winner of the Museum of Science Fiction's CubeSat contest to burning up upon re-entry of the atmosphere. CubeSats like CayugaSat that have solar sails have many possible uses in space. First of all, they could be launched together, and when they're all deployed, they could link up, forming one big solar sail. This solar sail could be propelled by the sun, or it could have lasers pointed at it, thus exploring the rest of our galaxy. CayugaSat's potential uses are as infinite as the universe. For one, it could be used for tracking asteroids or for cleaning up space junk, which is a big problem in the space community. Our teaming approach for designing CayugaSat was not that complex. I had the idea, after I heard about the contest, to design a solar sailing CubeSat. I didn't really know what I was doing, so first I made a club. I wasn't really expecting anybody to show up, but after I put up my flyers, about 10 people showed up on the first day. We got right into it, and we started talking about ideas. In the club, for the first few meetings, we discussed all of the different components that would be needed, and we talked about various designs. After coming up with a basic design, we divided ourselves into 5 subcommittees of power, deployment/sale, communications, physical design, and mission design. We all worked together though, even though we had our own subcommittees. If CayugaSat successfully uses its technology to display its solar sail, it could help lead the way in a new generation of solar sailing satellites and space exploration vehicles. Though typically confined to the role of a muse for science fiction writers and space exploration hopefuls, solar sails provide a new technology that can lead human space exploration around our solar system and far, far beyond.